not? Yes, we are getting sound. Okay. So first, a couple of announcements. One, the important one, is that there will be no class on Tuesday, the 23rd of January. Instead, there will be a pre-makeup, if you will, a substitute class on Monday, the 22nd, at the same time. So I'm going to do noon to 2 p.m. or noon to 1:45, depending on how far I go over. And I will post on the website where that class is going to occur. All right. So right now I have to get a room, and they haven't gotten back to me yet on where that room is going to be. So I'm going to do that. 2, homework 3 is out. All right. So if you don't have a copy, come and get one. Don't be shy. Let's see. The other thing is homework 1 is graded and should have been handed back to you. It's still going around, so that's a good one there. The reason we won't have class on Tuesday, I'm going to be in San Diego giving a paper at a conference. The only other one I can foresee having to move is on February 8th. I'm going to have a talk I have to give in Monterey at 10 in the morning, and I'm going to try like hell to make it back in time, but I may not, that doesn't give me a whole lot of margin for error. What's that? Oh, please.
Don't want the challenge?
Of course. Come on. Besides, haven't you seen that book on my shelf, How to Fight Your Ticket? Come on.
Well, I mean, getting a ticket would be okay, but going off the road and rolling would not.
Please. I got good tires on the car. What's that? The speeding trolls are less easy to feed than the parking trolls. The parking trolls are really easy to feed. But anyway, okay. So with that, those are 2 announcements. I will be posting where it is. A couple of people have turned in the problems. Oh, okay. One of the things I wanted to say, videos. The videos show up in the video directory. If you'll notice when you click the link, it always says video / there's going to be a whole thing /video/ and then the file name. If you delete the file name and just hit return, it'll actually list all of the video files that are in there. And then you can just choose and click on whichever one you like. Right? Those show up probably 10 minutes after class, as soon as I put the file over. Editing the HTML to get it to actually show up in there is a little bit more challenging. A couple of people have said they're having difficulties watching them. You can download from the TechSmith website. You can download their camplay.exe, which is their Camtasia player, which will play the files very nicely, at least on the Windows platform. And it downloads as a zip, which is an exe, so you don't need install privileges to actually do it. So you just unzip it and run it, and it works just fine. Okay, so on anyone who's having problems finding a machine that they can run it on, that should help. The last thing is, some of you have not yet figured this out, but the office hours are also recorded. Which means that when you come to the office hours, I expect you to have at least sort of blazed through the previous one to see that I haven't sort of answered your question already. All right, so I don't mind spending time. I don't mind, if it's not clear, I don't mind going over it again and again. But what I do mind is being asked the same question that I've already answered. In other words, if you do your work, I will bend over backwards to make sure you get it. Okay? But what I will not tolerate is laziness. All right? I expect you guys to do it, to look, to try, to do it. If you don't get it, that's fine. Okay? But what I don't want is for you to expect, to be completely spoon-fed and don't even take the effort to look to see if the previous one was already spoon-fed. All right? So, I expect you to waddle up to the bar at least. All right? It's the least I can ask of you. Okay, so with that, are there any questions? Yes?
How's the homework graded?
It's graded out of 10, and basically I think it was 2, 2, 2, and 4 points. Because the last one was harder than the other 3. Yeah?
Are there solutions on the
The solution is now posted on the website, so you can go and look them up and see how they were supposed to be done. Any others? I've got 2 of you who didn't show up in my course list, and you're one of them, actually. Are you registered for the class?
Not yet.
Okay, that would be why. All right, and there's one other one who I don't remember offhand, but I will get there.
So we had a fair amount of fallout.
I don't know, actually.
But no, it's looking a little sparser.
It's definitely looking a little sparser. There's a couple of people in the front who are definitely still in the class who haven't sort of shown up yet. Yeah, so there's a few people who are sort of late stragglers. I don't know how much fallout, or I just don't know how much people are just saying, oh well, I haven't had a chance yet to come in, or they're less, they're not coming in because they can watch the videos. I'm not sure. I never do know. Okay, so the last thing we did, and we kind of rushed through it at the very end last time, was I started out and I said that, let's see, yes. We started out and we said, if we take my plant and I inject a pure cosine wave into it, then what comes out in a linear plant is going to be another cosine wave with its amplitude modified and a phase shift associated to it. Okay, that's for all linear systems. And we said, well, the first thing we could do is we can take U of S goes into my H of S, take everything into the Laplace domain. Okay, so I've got U of S goes into H of S, gives me Y of S. Y of S is equal to H of S times U of S, multiplication. That's why we do it in the Laplace domain. Saves us the problem of doing convolution integral. And we can shove in S over S squared plus omega squared for our sine wave input, and then vary omega to see what happens. The problem with this, as everyone knows, is, or as you should have picked up from last lecture if you didn't know it before then, is that because we use the one-sided transform, this assumes that the system is perfectly stationary up to and leading to the point at time 0, which means that we hit it with a step and then it goes. Yeah, Shell.
If it is in the light from negative infinity to infinity transform, would that be right?
No, well, then it would still occur at minus infinity and everything built for minus infinity is still at 0.
So isn't minus infinity like theoretical?
Well, it is. But the problem is you're still hitting it at some finite point in time. Okay?
Right. You're going from nothing to something.
Exactly. At some point you're sort of introducing the input. Where what you really want to look at is what happens in the long term. And you can actually, and in fact, you guys get the problem on problem 3 to do this with a relatively simple system. All right? And you're going to do this both by feeding in a sine wave and by doing the other method and showing that in the long term you do get the same thing.
Okay, what's the other method?
The other method is the one that you said was opaque.
Okay.
Yes.
I don't understand how that's true for every linear system. It seems like you could multiply the cosine, your plan could be multiplying the cosine by another function.
Multiplication is not a linear function. Right? Multiplication by scalar is, but multiplication by 2 functions is not linear. That would be nonlinear. Transcendental functions, nonlinear. Right? But any additions and any scalar multiplication are linear. All right, so if you have a system which is, which has a multiplication in there, it's no longer linear. All right, you're not doing it anymore. All right, so there are limitations to it. But any linear system, and for a lot of systems, you can approximate a nonlinear system at least within the region of the area which your trim condition or your bias point, you can approximate it very closely as a linear system within that region as long as you don't stay very far away. So if you put in a cosine wave with a relatively small amplitude such that it doesn't, move the system away from that bias point, even very nonlinear systems will look linear sort of in the near field, if you will. So it's still a very useful analysis, and for all the sort of tricks and things you can do with linear systems, I would suggest you take my other class, which is offered last quarter, that a couple of people survived in this class, and it's and that will teach you all the fun things you can do with linear systems, which basically takes, in some ways, it's sort of the companion class to this. It's 240, and what that does is it takes all the stuff and you go into full multidimensional systems and all the fun things you can do with them. That's Introduction to Linear Dynamical Systems. All right. Okay, so the conventional way we would do this to sort of figure out what happens when we inject a cosine wave into the plant is we would take our Laplace transform of our cosine wave, multiply it by the impulse response or the transfer function of our plant in the complex domain, and then do an inverse Laplace transform out and take it to the far field. That was take it till time is till all the transients have died out, and then see what's going on, and we would recover this. Okay. However, that's kind of a pain. So the other way we did it, this is the other method, and the other method is to break up a cosine omega t into its complex components, which is a over 2 e to the j omega t plus e to the minus j omega t, and actually do the convolution integral in the time domain. So if we do the convolution integral in the time domain, and all that becomes is u of t is equal to e to the st, where s is evaluated at plus or minus j omega, I do the convolution, and what I wind up with, as I put this in, is I can pull an e to the st out in front, okay, which allows me then to recover what looks like exactly the Laplace transform of any arbitrary plant.
Okay.
Yeah.
Why is u of t set to e to the st? I thought u of t was a cosine omega t.
U of t is a cosine omega t, which is a over 2 e to the j omega t, which looks like a constant times e to the st, where s is plus or minus j omega.
Okay, so then what did you do with the e to the minus st?
Plus or minus. I've got both of them.
Ah, okay, okay.
All right? So I do it both times, and I'm going to get an e to the st in one side and e to the minus st in the other when I break it both up.
Okay, so you're doing them separately, kind of?
Yes, well, they're linear, so I can do each separately and add them back, which is what I do here, actually. So
okay.
going from here, okay, I just show that if I have a u of t is of the form e to the st, where s is, in this case, j omega, and it's either a positive or a negative j omega, it doesn't matter which one I choose, okay, I recover an e to the st in front times an h of s.
So if u is the minus j omega?
Then it would be e to the minus
okay.
j omega t, right. So now, taking, what's that?
What happened to your a over 2, sir?
Right now, it's a constant that'll get pulled out in front, so I'm leaving. So now, when I'm just taking right now just the Laplace transform, just the convolution integral of an h of t u to the t minus tau, where u of t is the form e to the st. In our specific case, we're going to take s is going to be equal to plus or minus j omega. Right? So if I just take this part here, and I do the integral, I wind up pulling the e to the st in front and saying that therefore y of t is equal to an e to the st times an h of s. Okay, and I'm just going to evaluate s, in this case, is going to be a j omega. Right, because that's what I substituted in for. It could be anything else. It would work for, s equals 5 or minus 5. It would still work the same way. Right, that's just doing the integral using an e to the st form. Okay. Now I take that e to the st form that I said, and I said, look, anytime I've got a u of t in the form of e to the st, I can say that y of t is going to be equal to e to the st h of s evaluated at whatever that s has to be. Now I take that and I apply it back towards the definition that I had for cosine, the complex definition. So now I pull it in. Here's the a over 2 on each side. Here's the hs of t e to the j omega t evaluated at s equals j omega. And here's the s evaluated at minus j omega. Right? So now here are the two a over 2's, and here's the two parts of the cosine. Yeah.
So one of the things I don't see is it looks like h of s is in the frequency domain.
H of s is in the frequency domain. However,
Evaluating it, go ahead.
I'm evaluating it simply at any finite value. Okay, in this case, the finite value is going to be j omega. It's a complex number. H of s evaluated at s equals something is just a complex number.
So the result, okay, so we have h of s is in the frequency domain. We're evaluating in a particular s.
At a particular frequency, which changes it into just a complex number. That is all it is. It's a complex.
Just a number.
Correct. So if I go back here and I look at my y of t, okay, my y of t is going to be e to the st h of s, where s is going to be some complex number, something that I shove in there. It's a number.
Okay, and this form came from out of...
Just doing this integration
Right, from doing the convolution integral.
in the time domain.
The result of that is...
Exactly.
If you do that integral, you get e to the st times something that's in the frequency domain.
Correct.
Okay.
Okay, it just drops out of the form when we do it. Okay. So with that, I reassemble y of t as a over 2 h of s evaluated s equals plus j omega times e to the j omega t. So I'm just shoving in for s. Now this is still a function of t, right? This is just a complex number.
Okay.
This is just a complex number. And it's still just a function of t. So with that, what I wind up doing is getting, and there's the way that complex numbers, the magnitudes add, and the magnitudes multiply, the phases add. All right, so anything in the numerator, you keep multiplying the magnitudes together. Anything in the denominator, you divide. Anything for the angle, it's just the sum and subtract, the addition of all the ones in the numerator and subtraction of all the ones in the denominator. So if I look at this carefully, I can reconstruct this as h of s, s equals j omega, looks like a complex number that has a magnitude and some phase. And if I look back here, not that one, this one. If I look back here, I can take the 2 inside, e to the j omega t over 2 plus e to the minus j omega t over 2 is simply the definition that I had of a cosine omega t. Right? So what that leaves is I can factor out on the front the m e to the j theta. Right? So what that's going to do is the magnitude is going to be multiplied by m, and the phase is going to be offset by the angle, by phi.
If you go back a slide,
Yep.
I see that we have a complex number times e to the j omega t.
Mm-hmm.
Okay, how is that going to mess with the phase?
Well, because the complex number is written as m e to the j theta, right? Or m e to the j minus theta if it's your evaluating minus. So when you plug that back in and then factor it, you have y is equal to ma e to the j omega plus phi minus e to the j omega, the omega t plus phi. So then you pull it out and you get a phase lag and an amplitude change.
Right, and you're multiplying the two e's together.
Correct.
Okay.
So what that says is anytime I shove a cosine omega t in, what I get in a steady state is an amplitude change out, and the amplitude is nothing more than the magnitude of h of s evaluated at s equals plus or minus j omega. Okay? So all I'm going to do is in the complex plane, I'm going to run up the j omega axis, and I'm going to look at that point and say, what does my Laplace transform of my transfer function look like when evaluated at that point? All right? And I'm going to check that, and then I've got the angle. All right? Which, in essence, if you think about it, means, so I have, if I look at my transfer function as having a bunch of poles and a couple of zeros, all right, let's say this is my transfer function. Okay? When I'm going to run up the j omega axis, I'm going to stop and I'm going to evaluate at this point. Okay? What is the magnitude at this point? Well, it's the multiplication of the length of that line, and that line, right, divided by the distance to this one and that one. Right? That's what I'm saying when we say that the magnitudes multiply, that's actually what I'm saying. Okay? So you're evaluating at this point, and this point is moving up and down the j omega axis. And you're going to keep reevaluating it. Okay? When I say what the angle is, right, it's actually going to be the angle, if you will, to that one, plus the angle to that one, plus the angle to that one, minus the angle to this one, minus the angle to that one. Right? And it's going to result in, effectively, when you look far away, when you get really far, that's actually going to collapse to one thing. Yeah?
So wouldn't it be the multiplication of the zeros divided by the poles?
Multiplication of the zeros divided by the poles. Correct. I said it backwards.
Okay.
Okay. But yes.
Yeah, so the numerator and denominator stay the same.
Right.
Yeah, okay.
And so now, all I'm going to do, so I'm evaluating what h of s looks like when s equals j omega. Okay, and I'm running up the j omega axis to see that. All right, and this may or may not help you sort of thinking that I'm actually looking at the ratio of the lines and how far they are away. Okay, that may or may not help. But it's one of those things that's sort of relatively useful to see. Okay, for me, that adds intuition. For other people, it might not. Yeah.
So evaluating at this point allows us to not really think about the transients?
Correct. So all I'm looking at is in the steady state. Is I want to know what the magnitude is and what the phase change is. This is Bodhi. This is exactly Bodhi. Okay, and this will later we will get very formal about how we do this. Give you a whole bunch of rules of thumb, and it will allow you to I can throw it something very complicated at you, and all of a sudden you'll be like, oh, no problem. This actually it looks like I'm going to plot the magnitude. I'm going to say, oh, I won't even have to draw this. I'll be like, oh, well, this is just going to do this, that, that, and that. Okay, there it is. There's the magnitude plot. And you'll be able to sketch this out about that fast. All right? Maybe, and then you'll look at the phase and you'll say, oh, okay, and the phase is going to do, let's see, it's going to start at minus 90, and it's going to go, and around here it's going to drop to minus 270, and there it is. All right? And you'll be able to sort of look at this, just, sketch these out really, really fast. And then, of course, these will be approximate. When you want to really evaluate what's going on, then you fire up MATLAB. But again, you want to be able to draw these by hand first, so that when you fire up MATLAB, if you see something that goes, if you see something that looks like that, you're like, okay, that's about what I thought. If you see something instead that looks like, you'll be like, it doesn't look right. Yeah, maybe I'd better check my transfer function and see what I did, right? Because I did something wrong.
What's the x-axis?
The x-axis in this will be log frequency.
Okay.
And this is going to be log of the magnitude,
Okay.
and that's usually expressed in decibels. Some people express it in decibels, some people express it in ratios. So either it will start at 1, the magnitude of 1, or it will start at a magnitude of 0 decibels, which is the same. Depends whether your roll-off is going to be at 0.707 or whether it's going to be at negative 3 decibels. It depends on which way you're comfortable doing. Okay, it's not one way or the other. All right, and the phase is always the phase. The thing is log omega going that way. Okay. So does that sort of clarify a little bit what's
that was great.
What's going on here? Everyone else sort of good and clear on this? Good, because it is important. It does come up a lot. It will become the basis of one of the the techniques that we use. There's actually 3 techniques that are wrapped up in this. Okay, Bodhi is the most common, all right, and in the sort of the easiest to understand. Nyquist is just another way of looking at Bodhi. Okay, Nyquist takes, so these are both linear plots in frequency. Nyquist plots one against the other. All right, and that sort of, you get these weird loops that go to infinity and things like that, and you wind up looking at things that way. And then there's something called a Nichols plot, which is a linear plot of one against the other as opposed to a log plot of one to the other, which has some different characteristics. All right, but these are both things that you can do. One of the nice things about the Nyquist and the Nichols is you can actually evaluate nonlinear functions directly, as opposed to simply looking at the ones that are just linear. And even though all the tools we develop are for linear systems, it works just the same way, which is a fairly powerful thing. Okay, so with that, let's launch onto some new material. Actually, I'll keep this in case I'm going to start snoring. All right, so the 2 points that I want to make before we start is that, here we are at the end of the second full week of class, and already we've actually come sort of a fairly long distance, although you may not have appreciated it at the beginning or while slogging through your homework. But the idea is that all of a sudden I can take the Laplace transform of my equations of motion, and that can get me to a y of s, which is equal to some h of s u of s. And then I can go, okay, u of t is an impulse, then that gets me that u of s is equal to 1, and that means that From here, I get the poles of h of s, and this gives me the building blocks of the response. The other thing is I can now know how to look at this and say that if u of t is equal to cosine omega t, I now know how to extract y of t is equal to m cosine omega t plus phi, where m is the magnitude of h of s evaluated at s equals plus or minus j omega, and phi is the angle of h of s evaluated at s equals j omega. All right, so I now have these two different things, okay, that I know how to do, and I know how to do them very easily now. Okay, this is something because, you know, once I have the transfer function, so once I have the equations of motion in their differential equation form, how hard is it to turn it into a transfer function? Yeah, not very, right? Everywhere you see a dot, put an s, rearrange it, you know, you get into a fraction, done. All right, so that's pretty easy. Okay, how hard is it to evaluate the magnitude of that for some complex number? Pretty simple. All right, takes a little bit of sort of getting used to, but pretty straightforward. All right, and especially, you know, if you're willing to go far enough to fire up MATLAB, you know, trivial. All right, so doing this in requires a little bit of complex math, but not a whole lot. So these bifurcate into our two areas. So one will lead us into the root locus method, and two will lead us into our Bode design method. And these both have things they're good at and things they're bad at. Okay, transient response. This is something that root locus is really good at. Rise times, overshoot, how much wiggle you get, things like damping, really good. Get that in root locus. Okay, very well. Tracking performance. Tracking performance is something that you get out of the Bode style. Okay, that tells you, you know, what is my bandwidth? How fast of a signal can I actually keep track of, and how far do I fall behind? All right. At what point, if I'm trying to chase a moving target, at what point do I start to lose the target? All right. At what point can I no longer stay alongside of it? Okay. Now remember that we can do this, by the way, by going up to here and sort of keep putting in different characteristic things for you and say, okay, let me see, how well do I track a step? Okay, I track a step really well. Okay, zero steady state there. How about a ramp? Okay, so I've got a continually changing thing that I'm trying to track, and am I falling behind it? Am I caught up? Am I right on top of it? Okay. What about a parabola? What about a cubic, etc.? I can just keep shoving in different things for you and finding it that way. Okie doke. So now we're going to it's going to take us a little while to get there, but there's a few things we're going to do in between, and then we're going to see sort of how it goes. We'll start with some block diagram algebra. So it's a little tedious, but you wind up having to use it to simplify when you've got fairly complex things where things are injecting over in different places. You wind up using this a bit. So I have, for instance, the typical one I draw is that U of S goes into H of S and pops out Y of S. So here's a typical one. And here's another one that I've been drawing a lot of, where I say my command Y of S goes in with an addition. Here I'm at my error, which is also a function of S. I go through some compensator, which gives me my control signal, which goes into my plant, which gives me out my Y of S. That comes back and it goes through some sensor model I have, and then that sensor comes back in and subtracts in to give me my error. Okay. So this is a pretty typical block diagram. And the question is, how do I reduce this to a transfer function? Right. The easy way to do this is, or let's say the long way of doing this, is to go through and say, well, let me just work out what each of these intermediate steps are. Okay. I've got that y of s is equal to, and because we're doing this in the Laplace domain, this is all just multiplication. Okay. So y of s is equal to g of s times u of s. All right. But what is u of s? U of s is equal to k epsilon of s. All right. So u of s is equal to k of s epsilon of s. So I say, oh, okay, no problem. But what's epsilon? Epsilon of s is equal to y c of s minus h of s y of s. All right? And therefore, I can do some rearranging and substitution. So now I'm going to put a k in front of these guys. Right? So I'll take this, shove it into that, and then take that and shove it into here. Right? And if I do this correctly, I'm going to drop the s's just because it makes my life a pain. I'm going to find that u is going to equal to kyc minus khy. And therefore y is equal to gkyc minus gkhy. Bring that over, and I've got that y c over y is going to equal to y over yc, that's the other way I want to do it, is going to equal to gk on the top times a 1 plus gkh on the bottom. Right? Pretty straightforward. Not bad. You can always do this. Right? You can always go through and assign variables for each one. Just go through the blocks and work it out. Right? Back substitute in, and you're done. However, there are a couple of shortcuts that make this a little bit easier. What generally you wind up doing when you try to reduce block diagrams is you reduce them all to these sort of little atomic pieces that you can't get things any smaller, and then from there you then sort of go through and apply your signals and work it out algebraically. So, the shortcuts. 1, if I've got G1 then goes to G2, this is the equivalent of a signal going to G1, G2. Now, this one, in this case, G1, G2 is fine. If these were actually matrices, block-oriented, it winds up being G2, G1, not G1, G2. So this is just something to know. For whatever reason, matrix multiplication goes backwards as opposed to forwards, and I think we have Newton to thank for that, but one of the other guys, I don't know. Some long-dead mathematician who screwed up everything for the rest of us. Okay. So this one, G1, G2, just you get to multiply the two together. If I've got a split where I have a signal that goes through G1 out like that, this is equal to G1 plus G2. Now, so these two should be fairly obvious. Here's one that is not so obvious. I have a signal that goes through a summing junction and then goes through a block like this and comes out. I can, if I want, move the summing junction after the block. But what I have to do then, the equivalent to this is, this goes G1 in here, and that goes with a G1 there. So if I move the summing junction past the block's got to be put in each path. Okay, that one should be fairly obvious. The last one, probably the most important one, is the feedback loop. So here's the one where I have U goes in, plus, minus. I've got a G1 in the forward path, and I've got a G2 in the rearward path. And this one is equivalent to the forward path over what is referred to as the 1 plus the loop gain. If it's minus, it's plus. If it's plus, it's minus. Right? So it's 1 plus, and we refer to, so it's the forward path on the top, and then the loop, 1 plus the loop gain on the bottom. The loop gain is what you get multiplying the path all the way around the loop. Right? In this case, it's going to be G1, G2. Okay? This one you use so often that it's that you wind up just memorizing it. So if this becomes a plus, that would become a minus. What's that?
It's similar. Is there a name for that?
That would be positive feedback as opposed to negative feedback. Very dangerous.
I was thinking in my circuits classes where you take, like, you can, across an op-amp as a feedback, you
right.
can make it to equivalent on either side, and then similar forms.
Well, yes, an op-amp is exactly implementing this feedback loop. Exactly. Don't remember it, but hey. Let's see. What's that? Anyway, this one, if you can always derive these, by the way, right? You can put the one, put a U here, put a Y, put a Y out here, put an epsilon here, and sort of just work it out, and you'll come up with exactly this. All right, you can always work it out.
Can you go back a page to number 3?
Yeah.
Now, I don't get what we're doing there.
You're taking the summing junction and moving it beyond the block. And to move it beyond the block, it multiplies both paths. So you have to put it in the forward, in the direct path, but you also have to put that block in the feedback path, or in the other branch that's coming in.
Why would you want to do that?
Sometimes you want to move you want to move a summing junction because then you can do things like collapse it into one of these. Right? Now, here's one that we're going to do for fun as an example, and it may be very similar to something you have on your homework. So suppose I have something that looks like this. I've got a U comes in. It's got goes into a summing junction with a plus. All right. It also branches off and goes this way through a block G2 and adds in here. So that would be a direct feed through. Okay. Here we've got this, which becomes G1, which goes and adds in here. This comes out to Y, and this picks off and comes back with a G3 and comes in here with a minus. So, how do we do it? Where do we start? No. MATLAB is actually relatively useless at hooking up block diagrams. It does have some stuff in it, but it's so clunky it's easier to do it by hand. You are almost never sure what you're getting. I mean, they do have this whole thing in there, but you have to be so careful about which inputs and which outputs are being hooked up and how to do it that it's actually far easier to do it this way. Sheldon looks shocked. He's like, MATLAB isn't good for something? All right, so first thing I do in this case is you start doing some labels. Right? So U, epsilon, Y. Let's take a look. All right. So let's just write down what Y equals. Okay. So Y is going to equal to an epsilon times G1 plus a U times G2. Right? So it's just going to be epsilon G1 plus U G2. Okay, there's the first one. Okay, now, what is epsilon? Okay, epsilon is going to be U minus G3Y. Right? Just tracing back, here's Y, that's Y. Y times G3 minus, plus a U. So I'm going to substitute in for here. This is going to be equal to U minus G3Y. Right? So I'm going to shove that one in. And I'm going to get that Y is equal to G1U. I'll make it capital to be consistent. G1U, right, minus G1G3Y plus G2U. Okay? Gather the Y's on one side, gather the U's on the other. So I've got, on the Y, I've got 1 plus G1G3 times Y, and the U's I've got G1 plus G2. Therefore, the transfer function, y over u, is G1 plus G2 over 1 plus G1, G3. Now, the transfer function I'm looking at is not always y over u. Sometimes I'm interested in what the error is doing as a function of the input, in which case I'd be looking for epsilon over u. Okay? Which is no problem. All right? All it means is I want to isolate epsilon on one side.
Your name for that?
Yeah, that would be your error transfer function. Okay, sometimes I'm going to have a disturbance coming in somewhere, and I want to know what, often it's called W, right? And I want to know what the transfer function from W to Y is, i.e. how much does this disturbance alter my tracking, alter my output, okay? Or noise on my sensor, okay? We'll also do all of these things. The transfer functions become useful. They will always all have the same denominator. Okay, the characteristic equation is going to be the same for every transfer function in the system. Only the numerator is going to change. Why is the denominator always going to be the same? Because the fundamental building blocks of the response are always the same. Those are the modes of the system. The system only knows how to. The system can only create responses that are of those modes. How much you mix them together is by which way the signals get injected into that system. All right? So, one other little clue. Here's one that if you've got one that looks like this, which is, say I've got something that looks like this. So, this can get a little hairy. All right, and you're like, whoa, wait a minute, what do I do now? All right. Well, this wire is just a signal wire. Right? So I can redraw this pretty easily as take that and move it to there. All right? And now that's the easy one, because then I can say, oh, wait a minute, this is just a feedback loop. I know how to collapse that block. All right, so I'll just collapse that block, and now I just got that block goes in two directions. The other way to do it is to do it this way. That would be the hard way. Okay, because now I can't collapse the block anymore. All right. So when you see this, you can always sort of, as long as it's on the same wire, you're still taking the same signal. All right, so you can sort of move it around. So if you do it the red, the red is bad, the green is good. Okay? We try to keep things nice and simple here. Bad, good, that's good. Okay, so if I take this, so I had originally the system was this, okay, which I don't know how to analyze, right, because it's going back, but it's also going forward and out, right? So there's nothing magic about this pickoff point. So I take this pickoff point and I replace it with two pickoff points. Still the same signal on the wire, right? But then I look at this and I say this is one of my canonical blocks that I know how to collapse this. I know how to collapse this. This is going to be, if this is minus and plus, that's going to be a G1 over a 1 plus G1. Okay? That goes in to G2, coming this way, and whatever signal coming out that way. If instead I take the same thing and I've got, what did I say, G1 here, and I do that, I'll eventually get to the same answer, all right? But this is going to be a lot harder. This I have to do algebraically, because there is no easy block I can collapse. All right? That's why we say red bad, green good. So moving it outside and isolating a block is a good thing. Moving it inside and giving yourself nightmares of algebra is a bad thing. So, okay. Now, we're going to go very, very sort of slowly and gingerly into root locus.
James?
Yeah?
So to collapse that block with the line coming back, it would be G1 over 1 plus G1?
This one right here?
Yes.
Yeah, that would be G1 over 1 plus G1. Okay? As long as that's a minus.
Yeah.
If that were a plus, it would be G1 over 1 minus G1.
1 minus G1.
Okay? And in general, using positive feedback with an unstable system to try to stabilize it, it can be done. There are times where it is useful to do it under but you really got to know what you're doing. All right.
When it goes wrong, it goes horribly wrong?
Yeah, and well, unstable systems tend to thrash around quite nicely.
Right, and if you're dumping positive feedback into
So when you're putting positive feedback, you're actually, the idea is, the positive feedback is the idea that two wrongs make a right. All right,
Yeah.
essentially,
Yeah.
is you're doing that. And, in spite of what, your grade school teachers tell you about, positive feedback is a good thing, and the controls were, is not. Okay, just so you know. And frankly, I have my doubts about the other one, too. So, anyway, there was a question somewhere floating out here, yeah.
Yeah, on the previous example?
Yeah.
Is there a way to collapse those two just using those properties you showed us?
Not easily. So the thing you can do here is, what I could do is I could take this signal and I could move it inside. I could move it inside here. All right. Now, in order to move this signal inside, I would have to put. This is moving a summing junction. No, there's really no. This one's sort of a nasty one that when you find yourself in situations like this is when you break out the signals and just solve it algebraically. It's not that bad, but there's no easy way to do it. All right. Let's start in on, as I said, very gently, we're going to start in on root locus. And really, these are sort of the background for root locus. So let's do it root locus slowly. So if I start with my standard thing, and I'm going to do 1 over s plus a here. So here's a pretty simple system, and I've got y of s. I know that this has a characteristic response that looks like an e to the minus a t. Okay? That if I hit it with a step, it's going to start at 1, and it's going to come down on an e to the minus a t. Okay? So, by inspection, right? That one's kind of easy. Now, if I wrap a feedback loop around it, and there are two sort of canonical ways to draw this, and there are some subtleties in between, though the algebra works out very, very similarly. Imagine this is, if you will, the control system. This is the response of an aircraft in flight. Okay? Pitch response of an aircraft. How are we doing on time? We're doing fine still. All right, so I have my input. It goes in. It feeds my aircraft, my plant. It has an output y, and then what I've got is I add a feedback path, and in the feedback path is going to be my autopilot. And what this is doing is, if you think of this, there is still a command coming in. This pilot is still flying. And what you've got is an autopilot that's riding shotgun with you. Right? And what it's saying is, listen, I'm monitoring the output, and based on the design of this, I don't like what I see, so I'm going to help you. I'm going to add something in that's going to sum with your thing. with your input. So you're going to get a little push of the stick from the pilot, and then the autopilot's going to say, oh, well, that's not really what you want to do. This is what you wanted to do, and it's going to sort of push a little and pull back a little and push a little, and that's going to ride on top of what you put in. Okay. So in this way, you can think of there is a co-pilot. In this case, your computer is flying your co-pilot, and it's doing things that it thinks is going to make your life better, easier. It's going to stabilize the plant. It's going to make it respond faster. Whatever it is that we decide we want to do with it, it's going to try to do. So far. Okay. So if the other canonical way of looking at this is I have my command input that goes in, hits my autopilot, which then hits my plant, and then has a feedback loop in it. Okay. What this is doing is saying, you are not flying the aircraft. The autopilot is flying the aircraft. You are instructing the autopilot what you want done. Okay. And then the autopilot is adjusting accordingly. Okay. So what you will see is the math in these is almost identical. All right. And it's kind of a subtle way of looking at the difference in the problem. All right. So I just wanted to sort of introduce that concept to you so you guys sort of see that there is a slight difference. All right. And the slight difference here is, the autopilot is riding shotgun. Okay, so I'm doing something, the autopilot is beside me sort of wiggling the stick, wiggling the control surfaces in such a way that it thinks is going to make my life easier. Often this is referred to as a stability augmentation system, SAS. If any of you have ever flown an RC helicopter before, you will discover they are impossible to fly without one. Well, there are a couple of people in the world who can, but they're really twitchy. They sort of blink a little at odd times. But almost all of them, they will actually put in an autopilot that helps. And all it does is it actually slows the system down and makes it better behaved. So then a mere mortal can actually fly it. And they actually have a little potentiometer on it, and you can adjust how much help you want. From like really a lot of help, in which case the thing flies like a brick, to where, I want almost no help at all, in which case, it's barely keeping it right side up for you. And that's it. And you can and as you get better, you sort of keep backing off and stuff like that. This one is a slightly different configuration. Okay, with this one, you don't control the craft. Okay, the computer does. All you're doing is instructing the computer what I want the end thing to do, right? And it says, okay, I got it. You want to do this? I've got it from here. Relax, have a cup of coffee. I'm in command. All right. So again, there are sort of subtle little differences between them. Now let's take a look at what the math does. Usually this is referred to as a regulator or a compensator as opposed to an autopilot or a stability augmentation. But again, it's subtle. Yes, Daniel?
So the second one, though, isn't the feedback going to really fight you hard to keep it how it wants it?
Not necessarily, in that you generally don't feel, it doesn't come back to you.
I mean, on the middle one.
On the middle one, this one. Yeah, you do. And sometimes they will decouple it. Sometimes they'll actually put it in with a spring, so you can feel it, but it doesn't kick it back at full force. It sort of depends on what the designer is trying to accomplish. All right.
So is in one case the computer have more controls than the other?
Nope. No, in both cases the computer has as much control. It depends on the game and where you put it. It's literally, if you work out the math, they're almost identical. It's almost a philosophical difference. As I said, it's a subtle one. Okay. Yeah.
The notation on the bottom left with the two parallel lines.
I'm just breaking this and saying that things upstream of that, there's no feedback going the other direction.
Oh, okay.
The signal is only flowing in one direction. I was just doing that to presume. And by the way, some of these do actually on aircraft, especially the big ones, the things called stick shakers, where they actually put a motor at the bottom of the control column, and when you're getting, those ones, by the way, fly this way. And when you're getting close to the edges of the control envelope, where it says, okay, I can fly you fine up to here, but if you go a little farther out, I'm going to have some difficulties, it actually rattles the stick at you to let you know you're pushing the edge. All right? And gives you a tactile feedback of the stick goes at you.
So it would do that if you start getting close to the aerodynamic column?
Yeah.
It would do that?
Yeah. So for instance, if you're getting close to stall, it'll shake at you or things like that.
Does that mean to get to that?
What's that?
If you push it too far.
Well, there are places. So sort of a side tangent thing that there's an area in which feedback control systems can be deadly. All right, and that is that a feedback control system or stability augmentation system will compensate for any disturbances that are occurring outside the aircraft. All right. In fact, it doesn't care whether the problem you've asked it to track a certain input, and it is going to do everything it can to track that input, regardless of what's going on. It doesn't care if things are happening outside that make that input more difficult to track. It's still going to do its best. And so there was actually a famous crash that occurred in icing conditions where a guy at a commuter plane was flying over Iowa, flew into icing conditions and had the autopilot on. In this case, the autopilot he had was something called a wings leveler, which just flies it maintains the roll so that the wings stay level and you're flying on your same course. And as the ice was building up on the airfoil, the plane was getting harder and harder to fly. The control system simply compensated for it. So as the ice was building up, it was working harder and harder and harder to fly it, but it was still flying it fine. Up until it got to the point where the autopilot could no longer fly the aircraft. And at that point, it did what it was programmed to do, which is it flashes a big red light, sounds the siren, and says, I am outside of the bounds at which I can control the aircraft. The plane is yours. And it hands it back to the pilot. Okay. The only problem with this point is that, well, the only problem at this point was not only could the autopilot not fly it, but no one could fly it. This plane was now unflyable. All right, and basically, as soon as it let go, the plane snapped into a roll and basically crashed on the ground, killed all 40 people on board, because there was no feedback to the pilot that things were sort of exiting. And what they've done since then is they give the autopilot a reduced range of actuation, and they say when it can't fly with this reduced range of actuation, it lets go, and you've got a whole lot more that you can throw by hand that presumably will allow you to recover control of the aircraft. 6 one way, half dozen the other, I suppose. But at least it gives you a better fighting chance. There are times where control system does not know what to do. So I don't know how many of you remember when there was the Aloha Airlines lost the cabriolet version of the Aloha Airlines, where it lost it lost about 16 feet of the roof of the 737 in flight. And they asked the pilot. The pilot managed to bring it down, land it, and I think only 2 or 3 people died, and they were the ones who basically were at the edge of where the roof came off, and there was a steward or stewardess that got sucked out. Was it? And the other ones were injured? I don't remember. It was about 12, 15 years ago. But they asked the pilot later, they're like, how on earth did you know how to fly the plane to bring it down? And he said, I didn't. Basically, I had 15,000 feet to gingerly learn how to fly this plane by doing very little as possible and trying to sort of see how it would respond and listening to the thing creak behind me as I was doing it. Because he actually didn't know what was wrong. He could not see behind him to know that there was wrong. He just knew all of a sudden the plane was bad. Right? And so he would sort of very gingerly sort of take this, and he actually landed it.
Did he try to slow it down and put it into landing?
I don't know exactly. There's a whole NTSB report on it if you want to read it. That does thing. Anyway, let's now get back to the math of this guy. Okay. So by inspection, from a 1 over S plus A, all right, we've got an e to the minus AT response. Okay, from this to this, done. Right? By inspection, don't need to do anything more complicated than that. So now that I wrap this feedback loop around it, let's go with the stick augmentation as opposed to the computer flies it. And as you'll see, it doesn't really change things much. But I'm now going to use my block diagram algebra, and I'm going to say that y over u, in this case, is going to be 1 over S plus A. That's the feed-forward path. And it's coming in with a negative feedback. So I'm going to have a 1 plus a K over S plus A. Right? So that's the full gain is K over S plus A. K times 1 over S plus A. I'm going to multiply up by the S plus A, and I'm going to get that y over u, in this case, is equal to 1 over S plus A plus K. So now this has a response of e to the minus A plus K t. So in this particular case, what I've done by adding this feedback is I can change the location of the root. Okay? And I can change it from an e to the minus at. If that was too slow, I can speed it up. If it's too fast, I can slow it down. All right? I can change this to pretty much, any e to the, I can change it to, it's still going to be an exponential decay, but I can change the speed of it based on adding this feedback. Now, let's do the other form. So now we're going to do this form. So for this one, I've got my y command goes in. Here's my k. Here's my 1 over s plus a. And now I'm going to put a feedback path here.
Okay.
Yeah.
So the other one was called changing the root?
Well, what we did was you noticed that what we did was we changed the location of the pole.
Okay.
By adding feedback. Okay?
Same as the root.
Yes.
Okay.
So the root of the characteristic equation is the pole.
Yeah.
And what I did was I took it from here, which was a minus a, and I moved it to wherever I wanted, which was a minus a minus k, or minus a plus k quantity. Okay? And I can move it back and forth. By varying k, I can swing this back and forth to wherever I want. Now, in this case, I'm going to do this, and I'm going to get, in the feed-forward path, I'm going to get now a k over s plus a, and the loop gain is going to be, now, whenever you see this line here, there's implicitly a 1 in here, right? So this is going to be a 1 plus k over s plus a, which is going to equal to, when I do the multiply up, I'm going to get a k over s plus a plus k. All right? So therein is the difference. As I said, the only difference here comes the fact that I now have a scaled output. Okay? That's it. That's really the only change that occurs. All right? So, what is the problem of making a huge, big, fat K? All right? I want this thing to respond, and I mean now. Okay? So I make a huge K. Okay? What's the problem with that? Overshoot? No, in this case it's an e to the AT response. There is no overshoot. All right? In real systems, yeah, you'll get ringing and overshoot. But something a little bit more fundamental. What is the K doing? If I look back here, okay, what's going on in here? What is this thing that's going in there to the plant? Well, the error, but the error is getting fed to. Let's look at this one a little bit easier. Okay, so here we've got an error. After my compensator, what's that? Well, it actually goes to my actuator, right? This is actually what's pushing on the plant. All right? So if I make a great big K, it means I need a great big actuator to go with it. Right? I've got to push really hard on the plant to make it do this. All right? And there's some fundamental limitations. All right? So
this is more a physical limitation than
correct. So there are implications. All right? When you design something that has to, shove a huge amount of energy into your system, you are designing something that's got to have a great big actuator to do it. Right? And there may be costs associated with that design, things like that are going to do that. All right? If you're doing it with an op-amp, you may find that you have to buy a better op-amp, a faster one. It'll rail. There's going to be implications in your design. All right? So there are things that happen. There's also some fundamental trade-offs in sort of control power and things like that. As I said before, you can you can try to take a Cessna and make it fly like an F-15, and it will for all of 0.2 of a second, but it won't do it for very long. All right? You don't have the energy available. All right? So these are things that. Now, what's the whispering back there?
She said Tuesday we could fly the Cessna for 10 seconds.
No, maybe. Okay. Well, however long it takes, it's not going to last that long.
Right.
All right. Are you sure I said 10 seconds last time?
I have no idea.
Oh, okay.
It was seconds as opposed to 10.
All right. Now, the thing is, the thing to note here is based on the feedback is that I can actually move the pole of the characteristic equation where I want. All right. So the question is, one, how do I do this? And two, more importantly, is where are the desirable locations? So even if I can figure out how to move the poles, it doesn't answer the question of, great, you can move them. Now where do you want to put them? All right, and why? All right, so one of the things that we're going to do, a typical client that you will get or control problem will be specified. Rarely will someone say, well, so here's what I want. I want a natural frequency of 4.5 hertz. I want a damped oscillation of this. I want a damping ratio of that. Almost no one's ever going to tell you that. What they're going to say is, well, I'd like the system when I ping it, when something comes along and whaps the system, I'd like it to be back where it was, about a second and a half. I don't want it to sort of ring for 10 seconds. I'd like to be there, pretty crisply. And, if you try to bring it back in half a second, it's probably too fast. So the person so basically there's going to be some time domain specifications that are going to have to be translated into these desirable locations of where you want to put them. Okay, so once again, let's take a look at the fact that, so I had in my case, I had S equals minus A. That was 1 over S plus A. And if I looked at this in the complex plane, here's the real, here's the j omega, this shows up at a pole at minus A. Okay, and this has an e to the minus at response. Okay, so all of these are equivalent statements. Okay, that S equals to minus A, the pole is at minus A, that it has a plant that looks like 1 over S plus A, that I draw it for you like this, or I give you the time response. These are all just different ways of looking at the same thing. So that's great. Now I'm going to look at the one that's a little bit more complicated, and I'm going to say, here's again my real, here's my j omega, and now I'm going to put 2 poles out here, okay, and I'm going to put these, they're going to be complex conjugates. I'm going to put it at minus sigma here, and at a j omega d up here. And what I'm going to do is take this, and I'm going to say that S is equal to sigma, minus sigma rather, plus or minus j omega d.
What's the little d?
Damped natural frequency.
Okay.
Okay? So,
hence the sigma.
yes. So sigma plus d. Okay. So now I'm going to write this as a 1 over S plus sigma plus j omega d times an S plus sigma minus j omega d.
Is that the sub d, right?
That's a sub d. Yep, j omega sub d.
Just making sure.
Okay? And if I rewrite that, it's going to be a 1 over an S plus sigma squared plus omega d squared. And I can also rewrite that as S squared plus 2 sigma S plus omega d squared plus sigma squared, like that, 1 over that. And I can also rewrite this as a more familiar way of seeing this is S squared plus 2 zeta omega sub n S plus omega n squared. All right, and what we can see is that that sigma is going to equal to zeta omega n, and that omega n is going to equal to the square root of omega d squared plus sigma squared.
On the red line, right there,
Yeah,
I see omega sub d squared plus sigma something.
that's sigma squared.
Okay.
Boink, up there. All right. Now, what this is effectively is just a translation between Cartesian to polar coordinates. Okay, all we've done. So let's look at this.
Can you go back to this?
Yep. I'm going to rewrite the relevant one, so it's okay. So from here, I'm going to have sigma. This is j omega d. So I'm going to leave the j off and just put this as omega d up here because it's on the j omega axis. Okay. And what we had was s plus sigma squared plus omega d squared was equivalent to I had s squared plus 2 zeta omega n s plus omega n squared. So
Go from omega d to omega n.
right here, you've got, I just take this and I multiply it out, and I've got s squared plus 2 sigma s plus omega d squared plus sigma squared.
Yes.
So omega d squared plus sigma squared is omega n squared.
Okay.
And 2 zeta omega n is the same as 2 sigma.
Now, omega n is the natural.
That's right. So omega n is exactly this, is the ray from the origin.
Okay.
Here's sigma, here's omega d. All right. And this angle right here, right, that's sigma, right? This is the sine of this angle. Let's do it blue. So sine of theta is equal to sigma over omega n, right? But sigma is nothing more than, so sigma here equals,
The absolute value of sigma? I guess it's
yeah.
Okay.
Sigma is equal to nothing more than zeta omega n, right? Therefore, this is equal to zeta omega n divided by omega n, or zeta. Which means that this angle up here is the arc sine of the damping ratio.
Is that a J or a zeta?
What's that? That's my zeta.
Theta.
That's your zeta.
That's my zetas. Yeah.
Yeah, he's looking at the one where you canceled the omega n.
Right.
Yeah, that looks like a J.
Very J.
That's my zeta. Like that. All right? So these are, so the thing is, in Cartesian coordinates,
There's a sine problem there? It's the absolute value.
it's the absolute value. Yeah.
It's the absolute value of sigma.
Let's see. It's just the magnitude of it. Since you never deal with negative damping anyway. I mean, you do, but we'll get there. So in Cartesian coordinates, I have sigma and omega d. Okay. In polar coordinates, I have omega n and zeta. All right. So these are just two ways of looking at the same thing. And zeta, by the way, has a very specific name. It's defined as the damping ratio. And when it is 0, when you have no damping, when your damping ratio is 0, you are on the j omega axis. And the thing will ring forever. When you have a zeta of 1, a damping ratio of 1, this is referred to as critically damped, and you are on the real axis, at which point you have no oscillation whatsoever. All right, so this is the way to look at it. Now, if I take
When you say it's the damping ratio.
the damping ratio, not dampening, damping ratio.
Damping.
Yeah.
Okay. It's the ratio of what to what?
It is the ratio of the oscillations to the steady state,
Okay.
is what it winds up being. Okay? And it's a...
It's how much oscillation you have in the envelope. So
Correct.
what do we think about? Okay.
Yeah. All right, so if I take my plant and I say that this equals omega n squared over s squared plus 2, zeta omega n s plus omega n squared, this is going to have an inverse Laplace transform of e to the minus zeta omega n t times sine of omega d t.
And that's e to the minus.
Zeta omega n
Okay.
t times sine of omega dt. What this means is, if I look at my envelope, okay, my envelope is decaying with an e to the minus zeta omega n, right? So that's an e to the minus zeta omega n, which is also an e to the minus sigma t. Okay? And the damped frequency, so if I look at the frequency between zero crossings, right, the frequency of that oscillation is omega d, the damped frequency. Okay. So, why are we concerned? Because this is how we're going to get our performance specifications from the time domain into the frequency domain, or rather, from the time domain into the complex domain. So once again, if I draw my real axis versus my imaginary axis, and I say, if I look at this, I have an e to the minus something, e to the minus at type response. Okay? As I take that pole and I move it out to here, I'm going to get a faster decay, still exponential. As I move this away from the real axis, I'm going to have that same oscillation, that same envelope, but now I'm going to have an oscillation that goes onto it. All right? And the farther I move away, the faster that oscillation gets. Okay? Same thing here. If I split it here and go up, I've got the same envelope, and I'm going to get, the farther away I move vertically, yeah.
Those are always envelopes because it's complex conjugate.
Correct. Right, because wherever you get one, you get another. So you get an envelope on the outside, and you get an oscillation in the middle. All right. So the oscillation stays within the envelope. Now, if I take a look at my step response of, I'm going to take my g of s, and I'm going to look at the step response. I'm going to take the inverse Laplace transform of this over s. So the step response of g of s, so g of s over s, right, is going to equal to omega n squared over, so I got omega n squared. I'm going to have an s squared plus 2 zeta omega n squared, omega n s plus omega n squared with a, there's going to be an s over there. And if I wind up doing the inverse Laplace transform, it's going to look like 1 minus e to the minus zeta omega n t times cosine omega dt plus zeta over square root of 1 minus zeta squared sine omega dt. Okay, so there I am. There's my thing. What does that actually look like? If I plot it out, what I'm going to get is my step goes instantly to a value of 1. Okay? My output from this is going to do something that rises up and oscillates down. So now out of this, I can say, okay, let's take a look at this. Now this isn't time, right? This is time going out that way, and this is y of t going up this way. Yeah.
So we have 1 minus e to the minus zeta
omega n t
times cosine
omega d
dt.
plus zeta over square root of 1 minus zeta squared sine omega dt. Right. So I'm going to look at this and I'm going to say, well, this is my peak overshoot, right? How do I find it? How do I find the time at which the peak overshoot occurs? Right, so I take the derivative of y of t, set it to 0, find the time at it. How do I find the value? Take that time, plug it back into y of t. All right, so I can do that. So now I can take my overshoot spec, which is how much I'm willing to overshoot my target before getting there, and I can turn it back into something that is a function of zeta omega n, and since omega d and omega n are related, I can turn it into something that's a function of those two. Likewise, I can say, well, what about my rise time? All right, rise time is a little funky, so people take different definitions. The definition that most people that we use is the time it takes to go between 10% and 90% of the response. Okay, so this would be the 10 to 90 rise time. We're going to call the time that it takes to do this the rise time. All right. So again, I can now say, well, I'd like to get it there. So how would I solve that? Well, I put in 0.1 there, solve. Put in 0.9, solve. Find for t at each case, subtract. All right, and then I've got that. All right. What about the other one that we use is a settling time response. All right. We say when. Now I know this is coming into a decaying envelope. Right. What I want to know is when does that decaying envelope get? When does the solution come in close enough that it never leaves, say, 1% away? Okay, so I want to be within 1% of the final. How would I do that? Well, that's easy. I just have to solve for e to the minus zeta omega nt equals, 0.99 or 1.01. Right? I'm done. Or actually, sorry, 0.01 is the one I want to find out. So as soon as that equals 0.01, that tells me that's going to cause my t settle. All right. So if you open the book to the very back, it's also in Chapter 3, we've worked these out, and we've come up with approximate solutions, and they are approximate. All right. And the reason they're approximate is understand that your design is always going to be, someone gives you some specifications, you have your system, you're going to design your spiffy controller, then you're going to try it out. And you're going to say, okay, does this actually work as well as I'd hoped? Do I hit the specs I need? Probably not. Refine, try again. All right, because your system is never going to be a pure second-order system. All right, it's always going to have lots of other modes, and there's going to be wiggling on top, and there's going to be some high-frequency thing going on top of here. It doesn't matter. All right, eventually it's going to be dominated by, if you sort of look at it from the 30,000-foot view, it's going to be relatively, there's going to be one sort of dominant response, and that's the one you're going to tune. So you tune that one, and you say, okay, is this good enough? Maybe, maybe not. Try again. So it's always going to be part of an iterative process. So the relations, by the way, just so you have these, is the 10 to 90 rise time is approximately 1.8 over omega n. The settling time to 1% is approximately 4.6 over zeta omega n. And the maximum overshoot is equal to e to the minus pi zeta divided by the square root of 1 minus zeta squared. Okay, so there they are. You can, you can work with these. They'll do fine. They're not, as I said, they're not terribly intuitive, but what it allows you to do is start sketching out in the complex plane where you want to be. So for instance, if I say, look, I need a rise time of a second or less, okay, that tells you that omega n, right, has got to be greater than 1, right? So what's that look like? When I take my S-plane, omega n, constant omega n, draws a semicircle. Right? We're going to ignore the part that's unstable because, well, it's unstable. Right? But constant omega n is going to look something like that. These are lines of constant omega n. And by the way, you can do something in MATLAB, do F-grid. We'll draw constant lines of omega n and constant lines of constant zeta. So the blue, these are omega n equals constant, and this is zeta equals constant. Right. So what if I tell you, I need a rise time that's a certain amount, and it corresponds to this line. It means that I have to stay outside of this. So anywhere inside here is bad. Okay? This tells me my rise time must be at least whatever. Right? Anything in here is slower, anything out there is faster. Okay? But then I tell you, well, wait a minute. I need a settling time that's a certain amount. Now, settling time is a function of zeta omega n or sigma. So constant settling looks like those. So say I have a constant settling time, okay, that I have to stay up, that says, all right, you stay to the left of this one. And then, on the other one, I'll say that there's an overshoot spec, okay, which I need to hit. And the overshoot spec is going to cause me to stay, let's do one in the, like that. Let's say I have to stay inside of that.
Yeah, okay.
Okay, so I have to stay inside of these two. So now, all of a sudden, I have a region that says, here is the boundary of my good design. Okay? So I have now taken, once again to review, this one comes from a overshoot spec.
And that's the M sub P?
Right, that's M sub P. Okay, that's my overshoot. Okay? This one comes from my settling time.
And that's the omega n constant?
That's the zeta omega n equals
Zeta
constant.
omega n constant.
Okay? That's T settling.
Right.
And,
the rise?
right, and then this one comes from my rise time.
Okay. So the settling time points to the vertical line.
Right.
Okay.
Right, and I matched the colors in case you didn't.
Okay.
So,
Well,
what's that? Yeah, all the colors match. Okay, now, so this defines the area in which I can put my poles. I now have taken my overshoot, my settling time, and my rise time, and I've converted this to desirable location for my poles. Now, within these desirable locations, if this is desirable, if I redraw this as something like that, okay, what's that?
I was just saying, that's weird looking.
So, if this is the boundary of my desired region, and I can put my poles anywhere in there and it's going to be good, what's wrong with putting my poles way out here?
Also energy, actuation energy.
Right, so there's trade-offs. So in general, when you get specs like this, you're going to want to sort of come very close to the boundaries and hug them. All right? So you want to barely make your specs. All right? You want to sort of push on the system as least hard as you absolutely have to make it perform the way you need to. All right? This is what is referred to as being conservative in your design. All right? Yes, if this makes it, so does this. Okay? But this has other implications. Okay? And they have implications that are a little hard for the thing to do.
Wait a second, conservative is going close to the boundary?
Correct. Conservative is hugging right next to your boundary.
Using less energy.
So you're doing the minimum that you need to do to meet your specs. Okay? And as soon as your specs are met, you say, okay, that's it. I don't need to tweak the system any more than that. Right? And that is that I'm not going for overkill. If you've asked me for a rise time of 5 seconds, all right, I'm not going to give you a half second. I'm going to give you 5 seconds. Maybe it's going to be 4.9, 4.7, but I'm not going to give you, a 1 second rise time. Okay. Overly conservative would be, too close to the boundary. So, and that often can be, and by the way, there are limitations to where you can place your poles. Okay, that are going to come out from the structure of the K block that you design. All right. So, in certain ones, you'll be able to move them in certain places, and other ones you won't be. There are going to be limitations. Sometimes you won't be able to do anything about it, and you're like, look, this is as close as I can get. Right? I'm sorry, but, either that or we need to do something different. Yeah.
So we're in this company that makes integrated circuits.
Mm-hmm.
I've been in my boss's office when he's reading a new spec a couple times.
Mm-hmm.
Just laughs because they typically give you like really liberal specs.
Right.
They'll ask you basically for everything they can think of.
Oh, sure. So they'll say, well, I want a rise time of 0. I'd like I want the system to be infinitely fast. I don't want it to ring at all, and I want it to be instantly settled. And you're like, great. Go find another, another engineer to work for you because I can't do it. All right. And if you find another engineer that will actually say that he can do this, I'd like to meet them. There are lots of different things. I mean, there's everybody sort of pushes against everybody else. There's a sort of a famous cartoon of something that's sort of all the different groups as they design it and what it looks like and things like that. Anyway, let us do sort of just a little bit of review here. And I'll... What's that?
Back one slide for like a second.
Yeah.
Okay. Yeah.
Right, so the settling is, if you look at this T-settle, it's zeta omega n in the denominator. Right? So the larger you make that, the smaller your settling time is. So increasing settling, so that's actually not a bad thing to do. So if I have my complex plane, okay, so a boundary that moves, so boundary, as I move this way, I'm going to get a shorter settling time.
Now, is that the zeta omega n boundary?
Yes. This is a vertical line is a constant zeta omega n.
So that's sigma, right?
That's sigma.
Sigma is it.
Right.
Oh, okay, that makes sense.
Right. So as I make sigma larger and larger,
Mm-hmm.
okay, I'm going to settle faster and faster. Okay. Now, notice that I can get rise time without getting settling. Right. How do I do that? If I go all the way back here, okay, if I make omega n really, really, really fast, okay, then the response I'm going to get is going to go. It's going to go. Actually, let me change the scales here.
For a long time, but it's going to have great rise time.
Right. I can make, if this is my step, I can make this guy go wee 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 wee. Super fast. All right, which means he's going to have great rise time. Okay, he's going to have horrible overshoot, but great rise time. All right, so it's a trade-off. All right, and you can't get sort of, there are things you can get sort of one but not the other. So if I look at this one, if I take this line and I move it outwards, right? If I take this boundary here, right, and I move it to the left, I get shorter and shorter settling times. Okay, which is increasing my damping ratio because it's increasing zeta omega n, the combination of the two. But if you think about it, it's increasing the real part of that which is making the envelope that decay much faster, which means I'm going to get to that 0.1, I'm going to get within 1% of the final value quicker because the envelope is decaying faster.
Yeah.
Okay.
So it's not necessarily increasing your damping ratio.
Not at all. Not necessarily. Exactly. Well, no. Well, it depends on what omega n is doing at the same time that you're pushing it. So this one is shorter settling times. Likewise, let me try something here. Ooh, I like that.
Straight edge.
Yeah. All right. So here's my real. Here's my j omega. So now what I need is a compass. If I have my boundary here, if I take this and I move this outwards, right? So here's my spec.
That's an omega n, right?
Correct. So I'm going to take this, and as I move this out, this is shorter rise time. Okay, so taking this one, moving it to the left, shorter settling time. Taking this one, moving it outwards, gives me a shorter rise time. And the last one, we'll do. Yeah, wasn't quite as straight this time. All right. This is the real, the j omega axis. So on this one, as I fold these inwards, so these guys are, there's actually rotating these lines towards the real axis. So as I rotate these down, I get less overshoot. Right. So this sort of gives you an idea. If I take this wedge and I narrow it down towards the real axis, I'm getting less and less overshoot as I go, right? Because my zeta is getting larger, right? My zeta is going from 0 towards 1, right? And therefore my overshoot is getting smaller and smaller. Likewise, so this one, shorter rise, and this one, shorter settling time. So it sort of tells me where my specs in time push my poles, my roots on the complex plane. Yeah, Gary.
Is it possible that shorter, let's say your shorter settling time is all the way to the left,
Right.
and it doesn't produce that, kind of like, it doesn't overlap with or define the shape with the rise time?
Right.
So what happens in that situation?
That means that one spec is, you're saying, I've got this on my j omega, and my settling time response puts it here, and my rise time response puts it here.
Yeah.
So in this case, the spec that drives it is going to be your settling time. Right? Those are going to define the good spots. Okay? Now, at this point, can I get any overshoot? I can get any arbitrary overshoot still by just riding up and down this line. Right? If I go way far away, I'll still get a huge overshoot.
Oh, okay.
All right? Whereas if I come down towards the center, I won't. Right? So having a good settling time response doesn't necessarily guarantee that you don't have a lot of overshoot. It just means that, it hugs the line quickly. It may very well do, something that goes like that.
Just like
One huge whomp, and then it's there. All right? Which, depending on your system, may or may not make for a very comfortable ride. Okay? Then sort of it depends on the system. All right, so we'll stop there, and we will continue.
So ideally you want it to be on the axis, like on the left axis or the real axis.
Not necessarily. If you are on the real axis, I can get a faster response by leaving the real axis. Right? And in certain systems, something like a 5 or a 10% overshoot on a real system that you're sitting on top of, you won't feel. It'll be so crisp that you're like, wow, this is great. It just suspension in your car, for instance. Okay, will have an overshoot, and that's okay unless you're driving it at resonance.
Okay.
Yeah.
On the homework you just handed in,
Yeah.
it's focused on
Old homeworks. Yeah.
usable plots to do these various things.
Yeah.
Were we supposed
I'm sorry, you're using the what?
The interval plot or the table?
You can use the tables if you like.
Okay.
I was thinking of what I was trying to say. The name.
Yes.
The name for the feedback.
Mm-hmm.
Miller.
Miller.
Okay.
I
You
don't
know
know.
how you say like an input gets Miller multiplied when you have a capacitance?
No, you know, I'm not familiar with that term, but that's quite all right. I hadn't heard that.
Yeah, I think we studied that in 171.
Did you? Cool.
There might be something that's specific.
You're done like in the first